Hey everyone, welcome to Learn History. So this is basically our first tutorial video, and I thought why not discuss something that causes problem to all the HSC students and also some SSC students too. So today's topic is organic chemistry. So before we dive into what organic compounds are, I think we should talk about some important things like hydrocarbons and catenation properties. So let's see what catenation property is. The property of an element by which it can form long chains by bonding together several atoms of itself is called catenation. So carbon has this catenation property. So as we can see in this example, numerous carbon atoms are bonded among themselves and have formed a long chain. So this property of an element of forming a long chain by bonding within themselves is called catenation. And as carbon shows these catenation properties better than any other element, the main chain of organic compounds are basically formed of carbon. So there was a question when we were in class 9 or 10 that why the chain of organic compounds are formed of carbon. So here's the answer. Then we have hydrocarbons. And hydrocarbons are compounds which are composed of hydrogen and carbons. So this here is an example of hydrocarbon. This is butane, and the main chain of this butane is formed using carbon, and the rest of the arms are fulfilled by hydrogen. So this is a compound which is totally formed of carbon and hydrogen. So this is a hydrocarbon. Previously, it was thought that organic compounds are ought to be formed by only hydrocarbons. But now we know that organic compounds are not exclusive to hydrocarbons, because in alcohol we have an oxygen. In case of say amine, we have a nitrogen. So like this one, CH3, CH2, NH2. So this is an example of amine. So in this amine we have a nitrogen. Organic compounds are not exclusive to only hydrocarbons. It can have other elements such as oxygen, nitrogen, sulfur, etc. in its structure. So now we can define organic compounds as substances or compounds containing carbon, hydrogen, or any other elements like oxygen, nitrogen, sulfur, etc. Clear? Next, we will see the classification of organic compounds. So now we're going to talk about the classifications of organic compounds. So organic compounds are of various types. So I have tried my best to include every single type here. So organic compounds are mainly classified into two broad subcategories, which are aliphatic or open chain and cyclic or closed chain. Let's first see the classification of aliphatic or open chain organic compounds. So, aliphatic or open-chained organic compounds are those organic compounds which doesn't contain closed chain. That is, the carbons are not forming any ring. Both sides of the chain are open. For example, this one. This structure right here, we have these two carbons, these two terminal carbons which are open. So this is an example of aliphatic or open chained organic compound. Then an aliphatic or open chained organic compound can be either simple or branched. So this one is a simple aliphatic organic compound since it doesn't contain any substituent groups. But if any substituent group is attached by replacing a hydrogen, then that becomes branched aliphatic compounds. For example, here we have a hydrogen replaced by a methyl group. So this one is a branched aliphatic or open chained organic compound. This can be named as 2-methyl butane. Then both the simple and branched aliphatic organic compounds can be divided into two more subcategories, which are unsaturated and saturated organic compounds. So these saturated and unsaturated are based on the presence of double or triple bonds. If an organic compound is only composed of single bonds between the carbon atoms, then that organic compound is unsaturated. That is, alkane is an example of saturated organic compounds. On the other hand, if the structure has one or more double or triple bond in it, then that organic compound is called unsaturated organic compound. So let's see. Since in this structure we don't have any double bonds, this one is simple saturated organic compound. On the other hand, in this structure we have a double bond in the middle. So this is an example of unsaturated organic compound. So this is butene, that is alkene, that is a type of alkene, or we can say 2-butene, since the double bond lies at the second carbon. We're gonna see this naming later, but for now let's focus on the classification of organic compounds. Now let's see the classification of cyclic or closed chain organic compounds. First of all, the cyclic or closed chain organic compounds are those which forms chain or rings with the carbon or any other atoms present in the structure. For example, a cyclic or closed chain organic compound may be benzene. Benzene is a closed chain formed by only carbons. Again, we have another closed chain or cyclic compound of this format where the two carbons are bonded to a single oxygen. So these two are cyclic or closed chain organic compounds. Then these cyclic or closed chain organic compounds are then subdivided into two types, that is carbocyclic and heterocyclic. In case of benzene, every single vertex of the closed chain is occupied by carbon. So this type of structures where the ring is only formed of carbons are called carbocyclic organic compounds or carbocyclic cyclic compounds. Then in this case we have the chain or the ring formed by carbons and an oxygen. So this one is heterocyclic organic compound. That is, the main ring is formed by carbon and another element. In this case, this is oxygen. So this is an example of heterocyclic closed chain organic compound. Then both the carbocyclic and heterocyclic can be divided into two different subcategories called alicyclic and aromatic. So in case of a compound to be an aromatic organic compound, it has to follow some rules. So let's see those rules right now. So to be an aromatic compound, a cyclic or closed chain compound will have to follow these rules. First of all, it must be a closed chain. Secondly, it should have alternate double and single bond. And if we look into the structure of benzene, then we will see alternate double and single bonding. Like we have a double bond here, then this one is a single bond. Then again we have a double bond here, another single bond, here a double bond, and here a single bond. Then thirdly, which is the most important characteristics, that it must follow Haeckel's rule. And what Haeckel rule states? Sorry, this will be Haeckel's rule. So what's Haeckel's rule? That is, a aromatic compound should have 4n plus 2 pi electrons. So if any compound follows these two rules but doesn't follow the third one, then it won't be an aromatic organic compound. So let's first discuss what pi electrons are. As we know, there are two types of bonds, that is sigma bond and pi bonds. In chapter 3, I think, of first paper, you guys have learned about sigma and pi bonds, and we have learned that sigma bonds can stay alone, but a pi bond cannot be formed without forming sigma bonds. So in case of a double bond, one bond is sigma and the other bond is pi, since there cannot be more than one sigma bonds between two adjacent atoms. So in case of these two carbons, one bond is sigma and another bond is pi. So what Haeckel rule says, in case of a closed chain compound to be aromatic, it must have 4n plus 2 pi electrons in its structure. So this n here states the number of rings. In case of benzene, the number of rings is 1. In case of pyridine, the number of ring is also 1. But in case of naphthalene, the number of rings are 2. So this n for naphthalene would be 2, whereas the n for benzene and pyridine would be 1. So let's see how we can calculate the number of pi electrons. In case of benzene, the first two characteristics are easily seen. That is, it is a closed chain compound. It has alternate, double and single bonds. Now let's see whether or not it has 4n plus 2 pi electrons. So here we have a pi bond. Then here we have a pi bond, and here we have another pi bond. So in this structure we have 3 pi bonds. And we all know a bond is formed when 2 electrons are shared between the 2 adjacent atoms. So in each pi bond there are 2 electrons. So in case of 3 pi bonds we will have 6 pi electrons. And according to the 4n plus 2 rule, where n for benzene would be the number of ring, that is 1, we should have 6 pi electrons. So yeah, benzene is following all of these 3 rules, and thus benzene is an aromatic compound. Let's see if pyridine follows all the rules or not. Here, in case of pyridine, we have the first rule fulfilled, that is, it is a closed chain compound. Then alternate single and double bonding. Here's a double, single, double, single, double, single. So the second rule is fulfilled. Then let's see if it follows Huckel's rule or not. Here we have 1, 2, 3. 3 pi bonds. So in case of 3 pi bonds, we will have 3 pi electrons. Sorry, 6 pi electrons, just like benzene. So according to Huckel's rule, the n value for pyridine would also be 1. So according to this formula, it must have 6 pi electrons, and we have calculated pyridine has 6 pi electrons. So the two values are equal. So pyridine is also an aromatic compound. Then let's come to naphthalene. In case of naphthalene, we have 2 rings. So the number of pi bonds here are 1, 2, 3, 4, 5. So in case of 2 rings, the value of n would be 2. And so according to Huckel's rule, there must be 4 into 2, 8 plus 2, that is 10 pi electrons. And here we can calculate in naphthalene there are 1, 2, 3, 4, 5 pi bonds. Each pi bond contains 2 pi electrons, so 5 pi bonds contain 10 pi electrons. So again, Huckel's rule is fulfilled. So all these 3 compounds right here are aromatic cyclic compounds. Clear? But this one has a bit of difference from the other 2 structures. In case of benzene and naphthalene, the total rings are formed by only carbons. So benzene and naphthalene are examples of carbocyclic aromatic compounds, since the ring is formed totally by carbon. But in case of pyridine, we have a nitrogen here. So this is not carbocyclic. This is heterocyclic aromatic compound. Clear? Okay, now let's look into some alicyclic compounds. So alicyclic compounds are those cyclic compounds which do not follow one or more than one rules which state whether a compound would be aromatic or not. So let's look into some examples. As this structure here, we can see this is a closed chain compound. So it is a cyclic compound, but the second rule which makes a compound aromatic states that the structure must have alternate single and double bond. But here all the bonds are single, so this is not aromatic compound. This is an example of cyclic alkene, and we can name it cyclobutane. Now let's look at second compound. Here in this case we have an alkene which has 2 double bonds. How we can say it's an alkene? Let's see whether it follows all the characteristics of being an aromatic compound or not. First of all, it's cyclic. Secondly, it has alternate single and double bond. But according to Huckel's rule, it must have 4n plus 2 pi electrons, where n is the number of closed rings. So here n equal to 1. So this structure, in order to be an aromatic compound, must have 6 pi electrons. But since we have only 2 double bonds, here the number of electrons, that is pi electrons, would be 4. So the third rule is violated, and that's why it's not an aromatic compound. It's also an example of alicyclic compound. Thirdly, we have another structure where the 2 carbons are forming a ring with an oxygen atom. So as this one is not showing alternate single and double bonds, so this one's also not an aromatic compound. So why did I introduce this one? It's because in case of alicyclic compounds, we may also have heterocyclic and carbocyclic configurations. In this case, the rings in these two cases, the rings are formed exclusively of carbons. So these are carbocyclic compounds. But in the third case, this ring has been formed by joining of 2 carbon atoms with a oxygen atom. So this one is heterocyclic alicyclic compound. Clear? Okay. So we're done with the classifications. Now let's look into some more definitions, such as homologous series. So a homologous series is a series formed by listing all the organic compounds having similar characteristics. And as example, we have alkane, alkene as different homologous series. So there are actually thousands of organic compounds. So if we were to study all of the compounds separately, then it would have taken us years, maybe 10 years to complete the whole study of organic compound. So what scientists did is they have gone through the properties of many organic compounds, and they have formed a series with compounds having similar properties, and they have listed down all those compounds in a single series, and that is called homologous series. For example, we have methane, ethane, propane, butane, and etc. And the list goes on, like pentane, hexane. So all these compounds are listed under the homologous series called alkane. So if we study the properties of alkane, we will ultimately go a long way in knowing the properties of each of these compounds. And a homologous series always has a common general formula. And in case of alkane, the common general formula is CnH2n plus 2, where n is the number of carbon. So in case of alkane, the number of hydrogens will be 2 more than twice the number of carbons. Let's see. In this case, we have a single carbon. So according to 2n plus 2, we will have H 2 into 1 plus 2, that is 4 hydrogens, so CH4. Similarly, if we write this in a molecular formula type structure, then we will have C2H6. So 2 2s are 4 plus 2, that is 6. So C2H6. In case of alkene, the common general formula is CnH2n. So if we write the structure of ethene in this format, it would look like C2H4. So see, 2 carbons, 2 into 2 equal to 4 hydrogens. So homologous series actually contain a common formula by using which we can know all the compounds of a common series. Clear? So this is the last topic of this video, and that is functional group. So let's see what functional groups are. The part of the organic compound which remains in the structure of the compound and governs its physical and chemical properties is called functional group. For example, in these 3 compounds, we have this structure in common, that is CH3CH2. This is an alkyl group. Here we also have CH3CH2. In this case, we also have the CH3CH2 part. But in spite of having these common parts, this compound is alkene, this one is alcohol, and this one is an aldehyde. Why? Just because of having the separate functional groups. So as the definition states, the part of the organic compound which remains in the structure of the compound and governs its physical and chemical properties is called functional group. So in the case of alkene, the functional group is carbon-carbon double bond. In case of alcohol, the functional group is OH. In case of aldehyde, the functional group is CHO. And due to the presence of these structures with the alkyl group, these compounds are showing different behaviors. So this carbon-carbon double bond is basically governing the characteristics of this total compound. Similarly, this OH is governing the characteristics of this total compound, and hence it is alcohol. Then, due to the presence of the CHO group, this compound behaves completely different from these two and it becomes an aldehyde. So this is what functional groups are. Now we have many functional groups of organic chemistry. Here are some of the important ones. Like in case of alkane, the functional group is carbon-carbon single bond. For alkene, it is carbon-carbon double bond. For alkyne, it is carbon-carbon triple bond. For alcohol, the functional group is OH. Then for aldehyde, we have the functional group CHO. For ketone, it's C double bond O, where the two arms of the carbon is fulfilled by what? Alkyl groups. Then we have acid, whose functional group is COOH. So thanks for watching this video. Hope you guys understood. And if you guys have any sort of questions, you can ask me in the comment section and I'll try my best to answer. So thank you.